Hello everyone. Good morning, good afternoon, good evening. The authors and invited guests, welcome to the technical session 15B. Myself, Anshika Jain, and this session would be moderated by me. I, on the behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you all to the 10th International Congress on Information and Communication Technology, ICICT 2025, London, UK. The 10th edition of the conference is being organized in a hybrid mode. The physical event was held on 18th February in London, UK, and the virtual event is being held through Zoom from 19 to 21st February 2025. I hope you will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations, and each presenter will be given 12 minutes for the presentation and 3 minutes for the questions and answers. On 10 minutes, I will raise a very gentle reminder. There is another request to all the participants that you stay connected with us till the closing remarks. If you have any query or any update, then you can write it to me in the chat box below. Just before we get started with the session, I would like to introduce you all to the chair for this session, Dr. Kaushal Shah. Sir is currently serving as an assistant professor in the Department of Computer Science and Engineering at Pandit Deen Dayal Energy University. He has a vast teaching experience of around 11 years. He's an active researcher in the field of information security, blockchain technology, cryptography, and smart grid. He has also published several research articles at reputed venues and delivered keynote talks. Welcome to the session, sir. Would you like to share a quick opening remark with us?
Yeah, thank you, Anisha. Am I audible?
Yeah, so you are audible.
Yeah, so I would give my best wishes to all the presenters. And as Anisha mentioned, please stick to the timeline, right? If you present your work within 8 to 10 minutes, I can have a lengthy discussion if I want, right? If you take more than 10 minutes, then question answer will not have sufficient time. So I request all the participants to finish quickly.
Okay. Thank you so much, sir, for your valuable opening remark. So we'll be moving on to the presentations then. First, we have Mohammed to present the paper title Deep Learning Approaches in EEG Signal, Classification of P300 Brain Speller Development, a Comprehensive Analysis. Are you there?
Yes. Do you hear me clearly?
Yeah, you're there. You may please begin with your
Yes.
presentation.
Okay.
Yeah, please start.
Okay. First off, it's a pleasure for me to be presenting my paper in ICICT 2025. We targeted a data set in an EEG data set that was made for a P300 brain speller. The data set subjected 55 participants to look at a matrix that contains letters. This matrix would have certain rows or columns that would light up, and this would change the EEG signal of the participant to give a P300 response. The P300 response is like a slight bump in the EEG signal that indicates that there was an excitation for an action that the user wants to perform. So the data set had recorded these EEG signals using 32 electrodes at a 512 sampling rate. That means like 512 samples in a second. And they did this blinking stimulus 15 times for each row and column. So the participants were given 6 words, two of which was brain, power, and if they wanted to spell a certain letter from each word, they would wait until the row that contains that letter to blink. And so when it blinks, their EEG signal at that time would be considered a target signal, because that's the signal at which we want to, where we detected the letter that we want. Of course, if another row was blinking and that row didn't contain the letter that the user wants, that row the EEG signal recorded at that time would be considered a non-target signal. And so they did this 15 times for each character on each row and column for each 55 participant. Of course, this data set had other tasks like the resting eye and the RSVP, but those were ignored for the sake of our research. Of course, the problems that we noticed from our literature review that we wanted to improve the accuracy of this classification, where we classify between target and non-target signals. And we also wanted to integrate more deep learning approaches, as most of the literature review, only one source actually used a deep learning model on this particular data set. The literature review had plenty of sources, but for the sake of this presentation, because I only have 10 minutes, I will only discuss two. One used an RNN neural network, and in conjunction with a convolutional neural network to extract some features from the 2D EEG signal. 2D here means where you have the number of channels, that's one dimension, and then the other dimension, you have the time samples. They use the convolutional network to extract some parts of the EEG signals as features, and then they used a set of rule-based fuzzy logic to extract more of these features. Then they used an RNN network to classify the signal to either target or non-target. Of course, they got an accuracy of 74. That's an average accuracy on all subjects, and an area under the curve score of 0.8. The AUC score is a metric that measures how good is the model distinguishing between these two classes, which are the target and the non-target. There was also another paper, a deep learning framework for P300-based brain PCI speller. They used also a CNN to extract from the 2D EEG signal. But the difference between us and this other source, that they didn't calculate accuracy or an AUC curve. They calculated a CER, a character recognition accuracy, which is basically where they ran the model, they trained it, and they actually tested it, much like how the data set was collected, in order to spell out the word, the characters of the word. And then they calculated how many letters we got right, and that would be the character recognition accuracy. They got a 96% character recognition accuracy. And so the only source that we can compare ourselves to as a benchmark would be the fuzzy deep learning for modeling uncertainty in character recognition using EEG signals. So our approach, the data pre-processing, we handed 2D EEG data for 55 participants. First off, we reformatted it. We extracted some, you can call them epochs, but they're not like machine learning epochs. They're more like samples, where the dimensions would be the channels, which is 32, by the time samples, which was initially 512 hertz per second, but that eventually got decimated later in our pre-processing pipeline. And the third dimension is the trials, because as we said earlier, we had 15 trials, and so we reformatted it in that dimension. After that, we performed baseline correction. At the time of the P300 signal, there is, of course, some background noise, some background EEG signals that could interfere with the P300 response. And so as a way to subtract or remove those artifacts, we took the 200 milliseconds before the signal started. We took the mean of those 200 milliseconds and subtracted it from our signal. After that, we applied a Butterworth bandpass filter. What it did, that it eliminated frequencies in our signal and only kept the frequencies between 0.5 hertz and 40 hertz. Some sources did this, like applied this same filter, but between 0.1 hertz and 20 hertz. Others did the same number. After that, we downsampled our signal. Initially, it was 512 hertz. The P300 is around 300 milliseconds. And so we decimated by a factor 12. And then we normalized our signal using a robust scaler. Of course, the signal has a very chaotic distribution. And other than having a very chaotic distribution, it's very different from subject to another. And so we use the robust scaler, which is a type of scaler that uses the median and the interquantile range to normalize our distribution. Of course, this eliminates any outliers and is the best scaler to really handle very large outliers because it uses the median. After that, we used a min-max scaler between -1 and 1 to make our training more stable. And then we split our data into training, testing, and validation. Validation, of course, was used to know when to stop our training. The methods we used are the following: an RNN, an LSTM, an artificial neural network, a transformer, and an LDA. The transformer was a basic encoder-decoder architecture with multi-head attention. And the artificial neural network, as you can notice, has a very high dropout rate. This is because the data is very chaotic and we needed a way to handle the overfitting that was apparent in most of the training experiments. Of course, the ANN achieved the highest testing accuracy by the transformer, but the LSTM and RNN networks showed the highest signs of overfitting. They would perform really well on the training set, but when it comes to testing, the performance would be very poor. These are the metrics averaged on all the subjects and for each model. This is regarding the accuracy. So as you can see, training accuracy for the transformer is the best, but when it comes to testing, the artificial neural network surpasses it. This is, of course, because we gave it a very slow learning rate and a high dropout rate. And this is the AUC score. As you can see, the RNN and the transformer are really good at distinguishing between the two classes. When it comes to testing, the artificial neural network surpasses each other model. This is the learning curve of the AUC score for the artificial network for all subjects. So as you can see, it's pretty consistent. Each training and testing AUC score is paired with each other. No like very heavy learning changes. It's pretty consistent. And so when we compare ourselves to the other methods, the fuzzy deep learning paper, we surpassed it in our accuracy, but we didn't surpass it in our AUC score. But when you compare our approach to its approach, you would find out they use more than 3 different models to classify, while in the other hand, we used only an ANN model that consists of 3 layers, and it got a better accuracy. Of course, we suffered from the bias that was caused by the imbalanced data in our RNN and LSTM models, and that what caused its overfitting. And these are other metrics that we measured. Of course, the LDA was a very classical machine learning model. It was very basic. It got very good training accuracy, but when it comes to testing, it wasn't very good because of the imbalanced data. That will be it. Thank you very much. Any questions?
Thank you so much for your presentation. So do you have any questions?
Yeah, anybody from the audience? First I always give chance to the people who have joined. If somebody is working in the area, wanted to know more or comment, suggest something, you are free to give your suggestions. Okay, so if there are no questions from the audience, Mohammed, you did a nice job. Mostly you covered everything in the given time, but then I was missing the objectives slide. I mean, what is it that you wanted to achieve? Wasn't that clear? You might have said it verbally, but I couldn't find it in a slide.
So what we wanted to achieve is that we wanted to classify those signals to either target or non-target, so that when we can classify a row or a column in our 6x6 matrix, we, at the end of the classification, we see which row had the highest count as being a target and which column had the highest count as being a target. And when we get the highest row and the highest column, that would map to a letter. And so we needed a classifier that can take a signal of these blinking rows and columns and say, okay, does this row or column contain the letter that we want to spell out? So that was the main objective of the data set and of each model that we developed.
Okay. Okay, so that's it from my side. We can go to the next presenter.
Okay. Thank you so much for your presentation. So moving on to the next presentation. Next, we have Angel to present the paper title Offline Reinforcement Learning Approaches for Safe and Effective Smart Grid Control. Are you there?
Yes, I'm here. Can you hear me?
Yeah, we can hear you. You may please begin with your presentation now.
Um, sure. Let me share my screen.
Yeah, you can share your screen.
Can you see my screen now?
Yeah, we can see your screen. You may begin now.
Okay. Hello, everyone. My name is Angel Peredo, and today I will be presenting on offline reinforcement learning approaches for safe and effective smart grid control. So this research look at how we can train reinforcement learning agents without live interaction, which is something critical for safety in power grid operations. So today I will show you the motivation behind using offline reinforcement learning, how we design our experiments, and the promising results we obtain. Um, so first of all, a power grid is essentially the network that delivers electricity across vast areas. It is what controls the flow of electricity and ensures homes, factories, and businesses have the power they need. And because they are so vital, managing the grid effectively, it's crucial, right? Uh, so this is where reinforcement learning offers a promising solution. Reinforcement learning is a branch of artificial intelligence that focuses on sequential decision making, which is exactly the kind of problem grid operators face. So instead of a human operator trying to control and balance loads and prevent overloads on the power grid, an RL-based system could learn how to make those decisions automatically and optimize the electricity flows. However, an issue with reinforcement learning is that it involves learning through trial and error, this trial and error approach, which might be acceptable for some applications, but it can be problematic for real-world power grids because a failure or any mistake during the model training can be very costly or even dangerous. So if an RL model tries something unsafe, such as sending too much current through a line, this could damage the equipment or cause an blackout. Um, so clearly, we cannot let an untrained system experiment directly on a real grid. So that's where offline reinforcement learning comes in. So instead of interacting live with the grid, the model trains on a pre-collected data set of past experiences, such as historical data from a real power grid. And we can get all the benefits from learning how to optimize the grid, but without the risk of harming the actual infrastructure. Mhm. So given that most previous work on smart grids were on online reinforcement learning, where safety is a real concern, we wanted to see if offline approaches could offer a safer but still equally effective approach. And that motivation brought us to two main research questions. So the first one is, can offline reinforcement learning match or even outperform strong baselines in power grid control? So since RL dominates existing studies, online RL dominates existing studies, our goal was to see if offline reinforcement learning could achieve comparable or better performance with this added safety benefit. And the second research question is, since offline reinforcement learning depends on pre-collated data, one major concern is that if the data lacks optimal or diverse examples, the model will struggle to learn and it results in making poor decisions, making poor actions. So that's why we wanted to investigate also how the data set impacts the quality of the results. Um, so for our experiments, we selected three state-of-the-art offline algorithms, which are decision transformers, conservative Q-learning, and batch-constrained deep Q-learning. And these are well-known methods specifically designed to learn from fixed data sets. And also for the online algorithm, we chose PPO, Proximal Policy Optimization Algorithm, as our online baseline because it's widely used and highly regarded algorithm for continuous control tasks. Um, and for the data collection, since we didn't have access to a real power grid data, um, we generated our own data sets in the simulated grid environment. So one data set came from experiences and action of a partially trained PPO model, which still makes mistakes, and a fully trained one, which made near optimal decision. And the other data set came from an untrained model that made random actions to simulate lower quality data. And our goal was to see how each offline method performs when given data of different quality and how that compares to an online approach that interacts directly with the grid environment. Um, so for our experimental setup, we use a framework called Grid2Up, which provides several pre-built power grid environments at different complexity levels. So we use a small, medium, and large environment, and this allows us to test whether our approaches scale effectively as the grid increases in size and complexity. And then for the actions we allow the model to take on the grid environment, we're redispatching, so adjusting the energy generation to meet demand and reduce load on certain lines, curtailing, so reduce the flow of energy and on overloaded lines, and storage control, which is managing the stored energy to help balance supply and demand. Then our episodes lasted for 500 time steps. So you can think of an action per time step, and the model is allowed to perform a single action at each time step. But this could end prematurely if any power line became overloaded. So it's not fixed to 500. Um, so yeah, the image over here, it's the example of the one of the setups we use, the small environment. It consists of 5 substations, 2 generators, 3 loads, and 8 power lines. So you can see the blue circles here are the substations, which are facilities that contain equipment to control how the electricity flows. Each substation typically has one or more buses, which you can think of as internal connection points where multiple power lines and generators can be connected. Green circles are generators, which are the one that produces the energy and feed them into the grid. And then the yellow circles are loads, which represent energy consumption, so such as houses, businesses, factories. And the edges connecting these substation are the power lines, which transfer the electricity between substations and loads. Um, so the second image is the second setup, the medium environment. As you can see, it's a little bit more complicated, more complex. It contains 14 substations, 6 generators, 11 nodes, and 20 power lines. So this setup adds more complexity to over the small grid. So we can test our RL models to see how they handle more states, more routing decisions. And then finally, this image right here is the third setup we use. So this is a large environment, a large power grid, which has increased complexity. It has 12 substations, 62 generators, 99 loads, and 106 and 86 power lines. So we use this grid environment to test the scalability and robustness of the algorithm in a more dynamic and a more realistic scenario. Also, as you can see, the image has some edges colored like blue, yellow, and red. So blue means the power line is operating within safe limits, so it's okay. There's no risk. Uh, the yellow edges mean medium congestion level or like moderate risk, and red edges mean significant high congestion level. So the line is near its maximum capacity. Mm. This image right here, as you can see, the plot correspond to our small, medium, and large environments. grid environments, and each bar indicates the performance relative to PPO algorithm. So a value of 1 means that it matches PPO exactly, and anything above 1 means better performance. And we can notice how in the small and medium grids, offline algorithms perform mostly like similar to PPO, or in some cases even better, showing they can match or even slightly exceed PPO. But the difference is in the large environment, where all the three offline methods surpass PPO algorithm. This black line right here represents the minimum and maximum values obtained. And also,
Sorry to interrupt you, but you have 2 minutes to conclude your presentation.
okay. So this image right here is the result we got from testing the algorithms on the two types of data. So training on expert data and the random data, like low quality data. And we were expecting that we got better results from the expert data, since that's one of the main concerns about offline, the dependency of requiring expert data. But surprisingly, we got better results from like random data, from taking random actions. Our hypothesis is that the diversity matters more. The diversity, it cover more like wide range of possible states and actions in the grid. And then, so yeah, for the conclusion, our key findings is that offline algorithms, they not only have the safety benefit, they also can perform just as good or even better in some cases than online algorithms. Uh, and also contrary to the assumption that it relies only on expert only data set, we observe that variety in the training data often led to better generalization and overall performance. And for the future work, we plan to explore more complex actions. So in the actions we allow the model to take were only uh, modulating the current, but we wanted to like make topological actions too, and also test on a more complex scenario, like a more realistic power grid. And yeah, that's it for my presentation.
Thank you so
Thank
much
you
for your
very
presentation. Sir, do you have any questions?
Yeah. So thank you, Engel. Uh, Anybody from the audience? Any suggestions? Any part that you want to know more? Okay. So let me. I have two questions. When you say online and offline, what do you mean actually?
So
What is
online interacts directly with the simulation, with the smart grid. So it takes action and receives some feedback, right?
so
Uh,
online is not simulation, right? It is uh,
no, it's simulation. Well, it's trained on a simulation, but if when it's deployed, it will take actions. And offline, it's when you collect a data set and it's trained on a data set, but there's no risk of taking suboptimal actions. Um, so we can train on actual power grid data, right? Which online doesn't have that capability. So online, while it's training, it will make some decisions, but it could perform incorrect actions and cause harm to the grid.
so online would be more dynamic in nature, whereas your offline would be static.
Yes, yes,
Am
that's
I?
correct.
Yeah. Okay.
Yes, correct.
Okay. And somewhere in your presentation, you mentioned something about reward. I couldn't get that
Um,
part. It is a reward to whom?
yeah, it's a metric to estimate how well we're performing on the grid. Uh, the reward is basically uh, it's like incentivizing the model to reduce the stress on the power lines.
So
So the less
incentives
stress
incentives would be given in which terms? I mean, is it an
as
energy or
I
yeah,
mean, the reward is a scalar value. It's
scalar
in
value?
reinforcement learning, the reward is similar, it's like the loss from like the loss. So in this
Okay.
case, the simulation provides how much stress we're giving to the power lines. So the less we stress those power lines, we get a higher value.
Okay.
That's yes.
Yeah. And all the nodes that you are considering here are static, right? Can mobility be considered?
No. They're substations. No.
Okay.
Uh,
Okay, that's it from my side. We can go to the next presenter.
Thank you so much. Thank you so much for your presentation. We'll be moving on to the next presentation. Next, we have Mohammed Sabiri to present the paper title on quantum and LECT codes from the constant cyclic and cyclic codes over the ring IFPR. Are you there? Mohammed, are you there? Yeah, I can see you, but please unmute yourself and continue with the presentation. Mohammed?
Yeah,
Yeah, you please may begin with the presentation.
you see my slide.
Yeah, no, we cannot see your slide. Please share your screen. Yeah, we can see your slide, I guess. Yeah, we do. You may start now.
Yeah, Mr. Sabiri, we can see your slide, but then it's on some
Yeah,
other page. Bring it
you
to
hear
the first
me?
page.
You hear me?
Yeah, I
Yeah, we
can
can
hear
see
you.
you.
Yeah,
Go,
I can begin.
Your screen is shared. Please share your slides. Yeah.
go to the first slide.
Yeah, please go to the first slide.
Yeah, now you can start.
Yeah, please start.
Good afternoon, everyone. Good evening. My topic is about quantum and acid decodes from the constant cyclic and cyclic codes over the ring of PR of V over Fm minus Vm minus V. Shor's work was a crucial step in the field of quantum computing, laying the foundation for quantum information theory. His work was crucial because it demonstrates how quantum information could be protected against errors. But quantum communication needs quantum codes. For this, in the past years, researchers have been continuously working on developing new quantum codes by generalizing existing methods to find codes with better error correction capabilities using CSS construction, which might lead to advance in quantum counting and quantum communication. In fact, the CSS code construction is one of the most interesting code constructions shown in the literature. In fact, it is the first construction method exhibited in the literature in the sense that one can derive families of quantum codes by applying such construction. In the same way, we look to give quantum codes by using the finite non-chain ring Rm. As you know, constant cyclic codes are an important class of error correcting codes that have been widely studied in classical coding theory. The algebraic structure presents many advances that can be leveraged to consist new quantum error correcting codes, particularly through methods such as the stabilizer forms in the classical codes in quantum coding. The ring Rm is a finite non-chain ring with m zeta I non-zero idempotent elements. For this, we have sum from 1 to m of zeta I equal to 1. And for x of Rm, x equal to sum from 1 to m of Si zeta I, where Si is FPR. FPR is a finite field or with PR elements. As codes over finite ring, a linear code C of length n over Rm is an Rm submodel of Rmn. In order to give the linking codes over the ring Rm and the finite field FPR, we define a gray map as follows. J is an invertible matrix of order m, and the application fee is an FPR linear map preserving distance. or linear code C of length n over Rm is beta constant cyclic if for any code word C0, Cn minus 1 in C, we have beta Cn minus 1, C0, Cn minus 2 in C. Beta is an element of Rm. We prove that every code of length n over Rm, C is exactly sum from 1 to m of zeta ICI. Ci are linear codes of length n over the finite field FPR, and O code C is beta constant cyclic over Rm if and only if Ci are beta I constant cyclic codes over FPR. Also, we prove that every beta constant cyclic code C is generated by f of x equal to sum from 1 of m of zeta I fi of x divided xn minus beta I, and Ci is generated by fi. And for a beta constant cyclic code of length n over Rm, orthogonal of C is included in C if and only if orthogonal of Ci is included in Ci for all I. We recall CSS construction. CSS construction is a method uses two linear codes C1 and C2 such that C2 is included in C1. We look to application for CSS construction in the case OC is a linear code of length over the finite field FPR of parameter and key day, such that C is an orthogonal of C is included in C, then there exists a quantum error correction code over FPR of parameter n2k minus nd. Let C be a beta constant cyclic code with parameters n, k, dl. Then if orthogonal of C is included in C, there exists a code of parameters mn, 2k minus mn, dh equal to dl, where dl is the distance minimal of C. Now we give some examples. For m equal to 2, we have two non-zero idempotent elements, zeta 1 and zeta 2. And in F11 of Z, the factorization of Z21, Z22 plus 1 is as follows. For F1 of Z equal to square of Z squared plus 1, and F2 of Z equal to square of Z squared plus 1, the code C is a theta constant cyclic of length 22 over R2. Phi of C is a code over F11 of parameter 44, 36, 3. As orthogonal of C is included in C, orthogonal of C also is included in phi of C, and there exists a quantum error correction code with parameters 44, 28, 3 over F11. Similar, in F5 of Z, we have the factorization of Z20 plus 1 as follows. For F1 of Z equal Z squared plus 2 and F2 of Z equal to Z squared plus 3, the code C is nega constant cyclic of length 20 over R2. Phi of C is a code of parameters 40, 36 over F11. So orthogonal of C is included in C, and then there is a quantum error correction code of parameter 40, 20, 32 over F5. In this section, we require some definition of SCD codes, and by using cyclic codes over the ring Rm, under some conditions, we give a simple method to find SCD codes. The relationship between cyclic codes and SCD codes over a specific rank forms a method basis to constructing high-performance linear codes. Or code C of length N over M is linear complementary dial if the intersection between C and its dial is reduced to 0. And we prove that for linear code C over Rm, that C is an LCD code if and only if so those CI are the components of the code C. So that is to say, the code of length N over FPR such that C equal to sum from 1 to M of zeta ICI. And if C or cyclic code, then C is an LCD code if and only if Fi is self-reciprocal and all monic irreducible factors of I of Z have the same multiplicity in Fi of Z and Zn minus 1. And if C or linear code of length N over Rm, then C is an LCD code if and only if pseudo phi of C phi of C is the image of C by the gray map.
Sorry to interrupt you, but you have 2 minutes to conclude your presentation.
Yeah. For M equal to 7 and N equal to 6 in F14 of Z, and for Fi of Z equals Z plus 1, then Ci are SC codes of length 6 over F14. So C is an SC, the code of length 6 over R7, and phi of C is a code of length 42, 35 2 over F13. Similar in F47 of Z, for M equal to 4 and N equal to 6 for Fi of Z equals Z plus 1. The code C is an SC, the code over R4, and phi of C is an SC code of parameter 24, 22 over F37. Here is some examples for codes concepts over F13. For example, for N equal to 7 and M equal to 5, for Fi of Z equal to Z squared plus 5Z plus 1, we have a code of parameter 25, 20, 35, 25, 3 over F13. The aim of this paper is to construct quantum error correction codes and assess the codes of length N M over FPR such that M minus 1 divides P minus 1. The first codes are obtained by using the gray map and the CSS construction from DL containing constant cyclic codes over M. The second codes are made in as the gray image of SCD codes of length N over Rm. In the next article, we wish to study other codes which neither DL contain neither self-DL in order to have other quantum codes which have good parameters. And thank you for your attention.
Thank you so
Here
much.
is some references.
Yeah, thank you so much for your presentation. So, do you have any questions?
Yeah, anybody from the audience?
Anybody?
So if there are no questions from the audience, let me tell Mr. Sabri that you are working on a very difficult problem, right? Because there were around 12, 13 theorems that you have stated. It's not a question, just a suggestion. If you can prove some of these theorems, then that would be, I mean, give some hint about the way you have proved. You have taken examples for the theorems that you mentioned, but then I couldn't find any proof. I hope it's there in the paper, but you could have proved one or two theorems in the presentation as well. Yeah, so we can go to the next presenter.
Okay. Thank you so much for your suggestion and presentation. We'll be moving on to the next presentation now. Next, we have Hector to present the paper titled Personalized Chemotherapy Dosing Through Offline Reinforcement Learning. Are you there?
Yes.
Yeah, you may please begin with your presentation. I'll just allow you. Yeah. Yeah, you
Can
may.
you see this?
Yeah, you can.
Okay. Thank you. Well, hello everyone. My name is Hector Lugo, and today I'll be presenting my research on personalized chemotherapy dosing using reinforcement learning. Oh, sorry.
Hector, we cannot.
So the
Yeah.
there you go. So one of the main effects is cancer does affect millions of people throughout the world and has a high significant mortality rate with this. And one of the most common treatments is chemotherapy. The thing of chemotherapy is that when the dosage is admitted, it goes throughout the entire body, so it doesn't really have a selective state for that. And another thing as well with chemotherapy is one treatment necessarily doesn't work for someone else, even though they might have like different reactions and different outcomes with this. So one of the research questions we thought of was how we can use offline reinforcement learning to personalize this to hopefully improve the survival rates while minimizing the toxicity of that. And one of the ways we wanted to do this was use decision transformers to compare different the RO algorithm with fixed dose regimens. Fixed dose regimens are basically just static dosages and see how well that compares for chemotherapy optimization. So you may be asking yourself, why even use reinforcement learning in the first place? Well, with reinforcement learning, it overall adapts to the different patient data we simulate, and it can learn from past patients through a trial and error approach. And this is useful because it can overall just optimize the treatment for overall better survival time and lower toxicity for the patient, and hopefully improve the mortality or decrease the mortality rate for this. And one of the methods it can be used, it can avoid the risk of using online learning in real patients. And the reason why we don't want to use online learning is because that requires real-time interactions with patients, and one that's unethical and that can cause serious harm to those specific patients in general for this. And in healthcare, of course, we can't just be just doing trial and error for that, which makes online reinforcement learning unsuitable for this case. So one of the methods we thought of was using an offline method called decision transformers. And with decision transformers, it basically uses offline data to make the treatment predictions for this. And it uses sequential decision making to get past and present experiences to generate new sequences to recommend the most optimal doses for this. And this is beneficial because we don't need real-time interactions with that, unlike online RL, and we can just use the simulate data to train the model itself. So in this slide, we have the experimental setup of how it was stated. Basically, we have the simulated patient data with the tumor size and the toxicity level. The toxicity level is basically the overall health of the patient, and the tumor size is just the tumor size of like the cancer tumor size in general. And the way it was set up was the tumor and toxicity went from 0 to 2, 0 being basically the smallest, basically no tumor at all, to 2 being the biggest, max tumor size and the worst health condition. And we set up different initial conditions for each simulated patient overall to overall give the AI model different robustness to adjust to different dosages based on the patient's response. And as mentioned earlier, we used decision transformers, and one of the comparisons we did was use PPO, which is a state-of-the-art RL algorithm, to see how well it compares against DT to optimize treatment strategies for this. And the way we had it set up for the length was we had a fixed number of steps, and if the patient passed or if the condition of the patient got worse with that certain amount of dosage, it would end for that. And with the reward is basically how the agent would learn overall for this. So if the survival time was increasing for that particular patient and the overall toxicity and tumor went down, the agent knew that it was doing well and it would give a positive reward. And if it didn't, then it would get a negative reward for that and be like, it would basically means don't do that. The patient's going through hazards. And this is useful because it encourages safe and effective dosing decisions for the particular simulated patient. So in this slide, this is just to get a better visual representation and overall better idea of how to look at this. So here we have the chemotherapy dosage being put into the simulated patient. And here is basically the tumor size and the overall health of that patient. And here with the calculation hazard, this is basically used to determine if the patient will, it basically gets the current state and the current action of that patient with that dosage to see if it's overall improving to go the next round time in months, or see if the patient's condition getting worse overall. And if the condition is getting worse overall, then eventually the patient will pass. And this is overall the reason why we need this hazard formula in general is if we didn't have this in particular, the AI agent will just give max dosages to the simulated patient. And sure, like the tumor size would go down, but the overall health of the patient would ultimately lead to the death of that. I mean, that's not what we want. The whole point of this was to aim to optimize the patient's survival time while minimizing the adverse effects for this. So here are the key findings we found with the research. We found that DT did outperform constant dose regimen, which is basically static dosages, and outperform PPO. And this did, we saw that it did improve the survival time and reduce the toxicity for this. And later on, I'll show heat maps also and give a different visualization for this. So in this slide, the x-axis is basically the comparison with PPO, one of the algorithms we were competing against, the decision transformer. And then the yellow is the constant dose regimen, which is the static dosages. The 0.1 is the lowest amount of dosage for that, and 1 is the max chemo dosage for this. And then in the top right, as you see, as mentioned earlier, we have the overall tumor size and the overall toxicity of the patient or the health of the patient. And since this goes from 0 to 2, this is a static, this is basically at the tumor size is barely there. It's going up, but it's not at its peak. And the overall health of the patient is not perfect, but it's not the worst either. So as we see that DT did outperform both PPO and constant dose regimen by a wide margin, and it had the lowest death percentage for this as well. Now, when we increase the toxicity and the overall wellness of the or the health of the patient to 1, which is basically the middle point, we still see that DT still outperforms PPO and the constant dose regimen, and still overall has the lowest death percentage as a whole. Now, when we increase it to basically nearly to the max, we see that PPO did slightly beat it, but DT overall is still comparable to how PPO did. And this is good because the whole point of using DT is to use an offline algorithm to simulate data, and we can still overall see that even when the patient's conditions overall it's worse, that it still performs just as well or nearly just as well as PPO. So here's another visualization of the heat maps. With the constant dose regimen, the bottom is just the initial tumor sizes for this, and the top is the toxicity. When we darker colors mean that the patient's more or less dying from these states, and lighter is that they're surviving with the upcoming months. We see that as it goes on, the overall patient doesn't really survive with this, with the constant dose regimen. But when we go to decision transformers, on the next slide, we see that there's more variance and that the DT overall still like fights and still has lighter colors towards the end to still perform, showing that it has more adaptability with this. So some of the current limitations we have with this is that this is based on simulated patient data. We would need real world validation to further on do more testing with the offline. And some of the future work we're thinking of was incorporating different genetic factors, and medical history, meaning different age, how different ages react, or if a family is known to have cancer, like cancer lineage, or of any like history like smoking and stuff like that in general. And this will overall help the model just refine the dosing recommendation overall, and overall just adapt and enhance the model to go with these different patient simulations. And using an offline method is also useful because say if a new dosage or a new chemo dosage does appear, we can already use the offline data from DT to train, and it's overall just a safer and more beneficial way of doing it. So yeah, that's pretty much it for mine. And is there any questions?
Thank you so much for your presentation, sir. Do you have any questions?
Yeah. Thank you, Hector. Anybody from the audience? Okay. So you did the comparison between online and offline in terms of accuracy. And I mean, what you concluded was both of them nearly performs equally. Am I correct?
Well, towards the end, when they were at the worst, on this slide, they nearly all like in this state when they were all at the worst, they nearly performed nearly the same, but DT still performed just as well as nearly just as well as PPO, and that's what you want because this is an offline method and this is a safer approach. But when we're doing the other comparisons, the DT did slightly perform better than both PPO and constant dose regimen. When it went to 0.5, when the states were when it had barely any chemo, not chemo, when the cancer was there, barely there, and the health was already decent, it performed much better.
So I wanted to understand the reason behind this behavior. Why this happened?
I'm assuming from what we concluded was that since the offline data, it was able to see the generate the action, it was able to see from the fully trained model on how to overall optimize the dosages. Because with DT, it does use an offline data set with the fully trained PPO to go through later rates.
Okay, thank you. We can go to the next presenter.
Thank you so much for your presentation. We'll be moving on to the next presenter. Next, we have Aryan Panchal to present the paper Survey on Non-Invasive Glucose Monitoring and Glycemic Detection Using Machine Learning and Signal Analysis Techniques. Are you there, Aryan?
Hello, am I audible?
Yeah, you are audible. You may please begin with your presentation.
Yes, I'll just share my screen in a second.
Yeah, please. Yeah, we can see your screen.
Okay, am I audible right now?
Yeah, you are audible as well. You may start now.
Okay, hello everyone. My name is Aryan Panchal and I'm from Rajiv Gandhi Institute of Technology here in Mumbai. And I'm here to present a presentation on a paper that we've done recently, which is survey on non-invasive glucose monitoring and glycemia detection using machine learning and signal analysis techniques. Here are the contents. We'll start with the introduction first, then we'll move on to the research motivation and the problem statement that we are addressing, then the overall objective of the survey, then what all physiological signals for glucose monitoring have been used, and then machine learning and deep learning in glucose monitoring, then what signal processing techniques are being used for glycemia detection, then a comparison of 4 papers. We've included 9 papers in total in the paper, but in the presentation we'll look at 4 papers. We'll look at the comparative analysis, then the challenges in non-invasive glucose monitoring, and the future directions, and then we'll end it with a conclusion. So as we know, diabetes is a very big issue, not only in India, but also in other countries. It's a global health challenge which affects millions of people worldwide. And the role of glucose monitoring is very critical for managing diabetes very effectively. The problem with traditional glucose monitoring is that the finger pricking is very painful, and repeated glucose monitoring using the traditional method may lead to firing of nerves or basically pain in that sense. So non-invasive alternatives using ECG, electrocardiograph, and PPG signals are emerging for continuous monitoring. And people have been using deep learning algorithms, convolutional neural networks, and RNNs, which help analyze these signals to accurately predict if the user is suffering from hyperglycemia or not. So the research motivation is simple. It is just to support the existing research which is currently happening towards finding relation between heart behavior and ECG, heart behavior, which consists of ECG and hyperglycemia. So why is non-invasive glucose monitoring important? I would say it is for improving patient comfort. It utilizes physiological signals such as optical, electrical, and biochemical properties. Machine learning enables accurate glucose estimation, and then promoting even real-time monitoring. This non-invasive method can be easily integrated into wearable devices, which do not require pricking, and they can deliver accurate results. Objectives of conducting this survey is to actually identify and analyze physiological signals for glucose monitoring, such as ECG, PPG, NIR, spectroscopy, microwave sensing, and bioimpedance, and then examine the role of machine learning and deep learning in glucose estimation. And then also to investigate supervised ML models and their application in glucose prediction. So this is a survey paper that we've submitted, and across all the papers, everyone has used different techniques towards addressing this problem. This is the comparative, I would say, analysis of the literature review of just 4 papers. We've used, you can see the paper title, authors, and the signals they've used. Some have used pure ECG, some have used combination of ECG as well as PPG, and what machine learning or deep learning techniques they've used, and the accuracy which is stated by them. I've also listed the key findings per paper, what they've mentioned, and also the challenges that they've faced. The challenges, what we realized was that identifying reliable physiological signals strongly correlated with blood glucose, and then developing highly accurate ML models, which are capable of handling the variability. While collecting the patient's data, that project actually we're working on is a final year project, wherein this survey is part of the analysis phase of the entire project. So whilst collecting the data set, many patients, they perform some movements which also hamper the ECG data and everything. So, collecting accurate data and creating an accurate ML model is very crucial when it comes to predictions like these. And of course, addressing data quality issues such as signal noise and variability across individuals, as I mentioned now. The future directions of this paper, it aims to be a one-stop solution for researchers and students wanting to explore the domain concerning hyperglycemia detection using physiological signals. This research has already been going on. We do have machines which can sort of predict the glucose value, or if you have hyperglycemia or not, using non-invasive methods. But the project that we're working on, from the patient data that we have, this survey paper actually sort of supports the existing research by aggregating those 9 papers into one single paper. So, the non-invasive glucose monitoring can be further enhanced by reducing reliance on the blood-based traditional methods, and improving early diagnosis as well. So I would just like to conclude by saying that this research on hyperglycemia using ECG signals and deep learning presents a non-invasive real-time approach to glucose monitoring. By leveraging deep learning, it enhances early diagnosis, continuous monitoring, and personalized healthcare, thereby reducing dependency on traditional blood-based methods. So thank you. I'm open to any questions.
Thank you so much for your presentation, Aryan. So, do you have any questions?
Yes. Anybody from the audience?
Anyone?
Okay. Aryan, what is it that is you want to create? I mean, will it be a device at the end, or what is it?
So currently we are focusing on the deep learning model wherein okay, so we have a overseas company also in collaboration with this project who has sort of given us the patient data supporting, like we have 130 patients whose ECG data is with us. And our goal right now is to actually create a deep learning model wherein we'll analyze the ECG features, let's say HRV, the heart rate variability, and the RR intervals and everything. And based on that, we'll find a trend, or we'll find a sort of a graph which would support this research that there exists a relation between hyperglycemia and the heart behavior that we are observing. And then using that data, we can create a deep learning model which predicts, based on user inputs, which predicts how accurate the user has hyperglycemia or not. So
Okay.
yeah, so till like in previous semester, we have completed the entire survey process, and we are currently building the model. We have achieved good results in that, but the research is still going on in that. Yeah.
Yeah, but then I think 130 would be a very small sample size.
Yes, sir. It's a small sample size. We are sort of developing the main logic for the code as of now, but we are slowly getting more and more data. Since it's a overseas company, there are certain regulations and NDAs that we have to obey. So, but slowly we are getting there.
Okay. Okay. Thank you, Aryan. We can go to the next presenter.
Okay.
Thank you, sir.
Thank you so much for your presentation, Aryan. So we'll be moving on to the next presentation. Next, we have Anastasia to present the paper, Typology of Purpose of Generative Artificial Intelligence Use. Are you there?
Yes, I'm here. Good evening, everyone.
Good evening. You begin with your presentation. Yeah.
Yeah, thank you. 1 second, please.
Yeah, we can see your screen.
So, yeah, amazing. So, first, let me introduce myself one more time. My name is Anastasia Vitviskaya, and I'm representing Kazan Federal University, and I would like to mention that I'm very grateful for you to the opportunity to be a part of this meeting. So right now, currently, we are working on a model of applying AI in non-formal education for adults. So while we were working on this model, we have realized that actually a lot of people are using AI, and to make our model working better, we obviously needed to understand for which purpose, like real people do use AI. Because, for example, we all know that AI tools can be used for different cases and for different occasions. And to create a real working model, it was crucial for us to understand purpose of real people, especially local ones, because this model originally was supposed to be for local adults. And of course, the information which you can see on the screen right now, it's basically common knowledge that we all know that there are a lot of AI tools which can be used for several things, but what is the amount of real people who actually do use the exact tool for exact purpose? And we've decided that by knowing this information, we will be able to predict where in the future people will be participating less, in which processes they will be participating less, where will be more automatization, and how actually we will be able to prepare adults for that. So they will be able to find a job in the future, or they will be able to find new courses which where they will gain new skills. So by having a full picture of real purpose, we are working on a plan right now. of implementing AI in lifelong learning. Actually, this research, which I'm presenting right now, helped us to understand how we can prevent our future failure as a humankind. So let's go back in time. Because of the COVID, a lot of online courses were created, and actually it became very popular to study online, to find new courses, new specialties, and to work on new skills. So actually part of our article is dedicated to a COVID influence on non-formal education and lifelong learning, based on different articles and statistics which we have analyzed. And of course, because of the COVID and the incredible amount of online courses, people, adults especially, they didn't have time to check the course, and it was the question of the quality of learning. So that is why our research actually was made, and the geography of the research is pretty good, and we've communicated with 750 people, and from different parts of our country. And this geography can show like the variety of local users. So we will be able to understand a picture which we have right now in our country. So we were able to find not only adults, but also school teachers, then university professors, also students, I mean university students and school students, let's say pupils. So this actually has shown a big picture of the situation right now. So if we move on, we have finalized that 98% of people with whom we were communicating are actually using AI on a daily basis for their learning. I mean, lifelong learning. So out of the school, out of universities. So actually, we had one more research on the same question in 2023, and the result was that about 64% of people are using AI for non-formal education, but like this research, which was made like a year ago, have shown that almost 100% of people are using AI right now. So this, what you can see on the screen, a real purpose for what our locals are using AI. So if we divide it into 3 groups, we can see that it's mainly creation, correction, and search. So having this information, we actually can say that these purposes will be maybe in the future, let's say that people will be less participating in these processes, so which can cause some problems. And to see the distribution of the use of AI, actually we have this picture. So blue color pupils, school students. Then with red color, we have university students. Then teachers from school, orange, green one, university teachers, and purple adults with a higher degree. So based on this picture, we can see that the top purpose, let's say like that, for AI use are creation of text, and search for an answer. So mainly, of course, we all can understand that AI helps us to save time a lot, but by using AI always and for finding the information and creating text, people might stop analyzing the information which they are looking for. And it's good when you have a tool to save your time, but where is the limit? And what this use of AI can, how it can influence on our educational system in the future. And maybe it should be a limit, because some of the research and articles right now are showing that school students and university students are using AI without thinking, and they're just copy pasting the information, which can cause a lot of problems in the future. So actually a question, it's yes, so what can be done in the future, like by us as educators, as researchers, to ensure that an increased use of generative AI in the processes which have been mentioned previously doesn't limit human participation or degrade human cognitive abilities. So as a final, for the next step for the future research, we are planning to see the progress of degrading cognitive abilities. So, and in our article, you will be able to find some advice, some next steps, what we can do to help people, to help adults in non-formal education, not actually adults, students and teenagers as well. So we definitely need to include to our educational system to teach people how to use AI, because unfortunately right now in Russia, we don't have a lot of courses in the governmental schools and the universities and on implementing AI. Also, it is very crucial to, really crucial to teach people to train their cognitive abilities. Examples you can see on the screen. And it's necessary also to explain that not all the professionals will be replaced by AI in the future. And we need to understand that there is a limit of AI usage, and people just need to remember about that. That's actually all I wanted to say. Thank you so much for your attention. If you have any questions or suggestions, I will be very happy to answer them.
Thank you so much for your presentation. Sir, do you have any questions?
Yeah, anybody from the audience? Okay. You mentioned many things about generative AI, but then, I mean, what is your take? Is it a good idea to use it or a bad?
Actually,
Binary
my
answer.
idea.
Yeah, I want a binary answer, good or bad.
You know, I believe in AI, so I would say yes, but
It is good.
we need to train people. Definitely, there should be more courses, more information, how it can influence us, how it can influence our future generations, so people will be aware of the situation which is happening right now. But I would say yes.
So once we start training people in this usage of AI, then they would become more reliable on AI. Don't you think so? I mean, the usage of ChatGPT, or there is one more that came, DeepSeek or something, which that would increase like anything. And then the thinking capability that people would have, would keep on getting reduced. So, I mean, is it really necessary to train people in this direction, or is it a good idea to stay away?
I think it's necessary to train anyway, because as for me, AI, it's not just a tool, it's our future reality. And, it's like iPhones or internet when it was created, like a lot of people were very suspicious on that. So that is why I'm pretty sure that AI will be a big part of our future, but we will see, maybe in 5-10 years, who knows. But yes, I do believe that we need to train people to help them to, let's say, survive in the
Okay.
future.
Yeah. Thank you. That's it from my side.
Thank you so
Thank you so much.
Thank you so much for your presentation. So I sincerely thank our authors for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on the behalf of the whole team, thank you for your support during this 10th version and all the previous versions of the conference. We will be happy to have you in the 11th version in 2026 as well. All the presenters would be getting their digital certificates through email within 2 working days. All the papers have already been forwarded to the printer. So the publication will be live within 6 months. So kindly cooperate with the team of ICICT 2025. Before ending this session, I would like to take a moment to thank our chair for this session, Professor Kaushal Shah, for chairing this session. Thank you so much, sir. This is a token of appreciation to the chair on the behalf of whole team of ICICT 2025 and Global Knowledge Research Foundation and partners. I would be really glad if you could share a quick closing remark with us.
Yeah. I hope I'm audible as well as visible now.
Yes, sir.
Thank you, all the authors, for finishing their presentation on time. And thank you, ICICT and team, for giving me the opportunity to chair this session. You started the session by the greeting of good morning, good afternoon, and good evening. I would say it's a good night in India. We have past 11 p.m. and it was a really long day, but then it ended well, right? I enjoyed all the papers that were presented. Thank you again for the opportunity, and all the best to all the participants for the future.
Thank you so much, everyone. I would request everyone to kindly turn on their cameras for a quick snapshot before we end this session. Thank you so much, everyone. Thank you so much. It means a lot. Thank you so much. Take care. Bye bye. Stay safe. Thank you.